Okay. All right. Good evening again. You're welcome to today's lessons. Um, if you came yesterday, that's pretty good because I introduced myself. My name is Michael, and I'll be the one taking you through the machine learning sessions, right? Exactly. Let me get started with this. So yesterday we did have a look at the overview of machine learning and the nitty-gritty, the components of it, the different types of models that are or make up a machine learning model. You get a different paradigms that we can look at when we want to develop a machine learning model. So we did look at all of that. We looked at something called the supervised machine learning. We looked at the unsupervised machine learning. We also looked at the semi-supervised, or what is most famously called as the reinforcement learning. And we had a very quick recap of what do you call it, each one of them and an example of where they are applied. And it was quite interesting. So today, basically what we are going to do is to continue from there. But as we are going forward, of course, we need to see the processes involved in building a machine learning model, right? Just like any other thing, when you want to build, there are a series of processes that you need to go through, right? And machine learning is not an exception. So while there is not a one size fits all in this situation, in the context of ML, there is some formalities or some processes that typically, if you tune your mind to follow, you would achieve your goal. Okay, we get to it. So a typical machine learning process, just as I introduced earlier, has series of steps, right? It starts from when you get your data itself, that's the raw data. And we looked at what raw data is the last time we met, and we said raw data or training data basically is data that we have that represents history. So data we deem as having associated inputs and then their related outputs, right? That we think that this data is good enough for a model to learn on it. And then based on what the model will find in terms of patterns, it can make predictions out of it. So getting your data is the first step in the entire process. Of course, it's highly dependent on data and it's highly dependent on the structure of the data that you are feeding to it. So you get the raw data and it can come from so many sources. It doesn't necessarily need to come from one source. It depends on what you want to achieve. So here you can see that we have this diagram here that is representing more like a database or a data source. And we have raw data here, just indicating that the data is coming from lots of sources. That is fine. Or even one source is okay. Now, when you get data, you do what we call as you apply a pre-processing pipeline, or you apply pre-processing to the data. Now, what is pre-processing? A series of steps that go into what we call as a pre-processing pipeline or a pre-processing step. It can start from when you wrangle your data wrangling. Okay, there are a lot of big things that will be coming out of this very session. So pay attention to me as I try to break down each one of them. There is what we call as data manipulation, or data manipulation is also a term that will basically encompass or be put under data wrangling, right? And the data wrangling, you do lots of things. You can do data cleaning, make sure that the data that you are having is of the appropriate types. Make sure that when you have null values and the null values, you truly understand that they are null and should be removed. You do remove them. Okay. Um, I made that statement because there is a reason why you would not want to remove null values. So essentially, data that hits your model is strongly dependent on your understanding of the data. Okay, so all these processes happen under the pre-processing step. So once the data is prepared, that is when you go to applying the machine learning algorithm to it, or the learning algorithm to the data. But if you look at what we have here, you can see that there is a cycle at the pre-processing step. So it's not a straightforward approach. You can spend time here, a lot of time here, probably even days here at this very step. Okay. It depends on the some data are really, really dirty. So you have to spend time there to make sure that it is of good quality before you proceed to training a model on it, right? And that is what can take lots of your time. So I think it was analyzed that on a survey that was taken, machine learning engineers did um, emphasize that time spent on data pre-processing alone is more like 60% of the job. The rest of the 40% has to do with building the model and then deploying the model. But getting the data ready for the model itself can take you 60% of the time. Okay. And it's very essential to also get that part right, else you go forward and then come back. You understand? So it's an iterative process so you get what's right. Then once you get that, you get your prepared data, you apply the learning algorithm to the data. Okay. So yeah. So the model you apply to the data is also chosen. So there are lots of machine learning models to choose from. You have series and series of them. Now, each one of them have their capabilities and each one of them fall under specific types. So we looked at supervised learning, we looked at unsupervised learning, we looked at reinforcement learning the last time. Now, each of these, right, have specific way of learning on the data. And so the data that is you're going to feed to them need to be of a certain structure first before they can learn with it. So when it comes to supervised learning, we understood that it's taking the input, history representing an input and their related output. Okay, historical data that is having input and its associated output. Then you represent lots of samples in it. Then you feed it to the model. And then you expect that next time when you pass in input alone, it should tell you an output. That's how the supervised go. Now, even under supervised, we still have a breakdown, classification and regression. So we looked at if classification, then the data that you are trying to predict on, or the column you're trying to predict should be of a certain form. It should be categorical in nature. If it's regression, then it should be numerical, right? Or quantitative. All these are forms expected by the models. That is why you need to choose the very algorithm you want to deal with, right? So once you get the algorithm, it becomes a candidate model. Like you now go through an iterative process again to train the model or train series of model of the same kind, right? Of the same kind means that they are fitting on the same problem. So they are learning to predict a classification problem. So you can choose 3 models at a time, and then you iteratively train them and then test them. Okay, if their accuracy is good enough, you choose the best one out of it, and then you move forward. Now, if the accuracy is not good enough, then you go through what we call as tuning. So you do a hyperparameter search or something. We'll look at all of that, but it's very technical. You just have to understand at this very stage that this process itself of getting the right candidate model is also an iterative process. Okay, sometimes a particular model may not work well with your data, and then you have to change the model and bring in another model. Or the model might work well, but you have the right parameters for it to learn on the very data you are given it. So you need to change the parameters a bit. That is what we call as tuning or searching for the right parameters. You understand? Then once you get it, you get a right model, or you get a right algorithm to learn on the data to produce you a very good candidate model. Then you deploy what you choose. That is a chosen model. So you can now deploy the model to production. That is where the software or the application layer now feeds on the very model that you have developed. So that's a whole lot of cycle to go through, right? Some processes will make you go back and forth. Now, in this diagram, you don't see a representation where you go from here to here, but it's possible in real life. So in real life, you may not go straight like that. It will not be a straight pattern for you. You can get to this place and then get back all the way to even taking the right data again. So you might get to machine learning development and realize that your data is not quite good. So you have to go and look at your pre-processing steps and understand that you haven't done anything wrong there. If everything is good, you try again, it doesn't work, then it means something is wrong with your data, or your data is not for the very case that you want to solve, right? So you're not predicting well. So it means that what you're trying to predict, actually your data set doesn't describe it that much. So you need to go back to data collection. Then you move all the way from here to getting the raw data, right? You do that until you get a very good candidate model to deploy, right? Now a use case. Imagine you are asked by your boss while working at a big bank, right, to develop an automated decision maker on whether to give a potential client credit or not. So you work at a bank, and then at this your organization or your bank, you've been asked to build a model that will be able to determine if a client that is willing to take credit should be given the credit or not. Now, how do you think you go about it? Okay, so you think through that. How do you think you go about such a problem? So the question in the first place is, what are you trying to answer here? That is one thing that you have to get right in the first start of your entire ML process. Question yourself based on the use case, on the case study, and then you write the question down and make sure that whatever you are doing answers the question. So what are you doing? In this case, you are trying to build a model to predict whether a customer should be given credit or not. Is that your question? Then what is your answer to the question? Okay. And your answer to the question now depends on a series of processes that you go through. Now you decide to choose a machine learning approach to solve this problem. So it means that you need to go through the machine learning life cycle itself. And it starts from the very point where you need to get the right data to work with. Okay. All these steps should be at your fingertips, or it should be something that, well, it comes with practice. You would know when you miss a step, but trust me, if you miss a step, going forward is even difficult, because before you get to a better model, you have to clean data. Unless the data is clean enough, then you can skip cleaning. And even that, you have to do a checks on it. So you need to get a portion in your processes where you check for the data quality. If the data is of the right quality and you don't need to do much cleaning, then you go ahead to whatever process is next, right? But if the data is not clean and then you jump to model development, you will never get it. It will never work. Okay, so these are some of the things that you have to take note of. Now, selecting the data involves getting what we call as features, okay? Now, the input to the model is what in machine learning terms we call as features. Okay, so if you want to describe someone, we say that what are the features of the person? Okay, we know that this person has an identity. Consider the identity as what we want to predict. More like an example is the name of the person, or the person as a whole being what we want to predict. Now, the features of the person is what will let us know who a particular person is talking about. Okay, so you can say that a person has beautiful eyes, he's 6 feet tall, he's a little bit thick, you get it, dark in complexion. All these are features of a person. Now, what do you use these features for? You use the features of this person to be able to tell their identity. That is exactly the concept we are dealing with here. So when we talk of features, in concept of data sets, it's basically your X's. So X1, X2, X3, where X1 represents some data point that somehow has a capability of predicting something, right? Exactly. I just hope that was explanatory now. I will show you more of that as we move forward, but you do have to ask questions at this point. If there are, then we can move on. Do any of you have a question to ask? Keep it coming. It's clear, right? Okay. So another thing to take note of, is that to get the right features, most of the times it either comes from experience, or if not for experience, you need to do a very good and quality think through of the problem itself. The questions you ask yourself on the case study will direct you, it will direct you to the features you are supposed to take. So as I gave an example on the human description case study, you know that if you want to identify someone or you want to identify a place, there are questions you need to ask. If you want to go to Kumasi, there are questions you need to ask. Where are you going to pass? Which town will you get to before you get to Kumasi? Right? What is the total population of Kumasi, or how big is Kumasi? You are doing everything possible to describe Kumasi, and all of those descriptions are features. Now, you know intuitively that these are the questions you need to ask before you get there. And so when you are on your way going there, you know exactly what to do. It's the same way. So by experience, you can know what you are trying to achieve. That is what you're trying to predict, and then know the exact features that will lead you to predicting that variable better. Hope that is clear. All right then. And still on selecting data, we move to what we call as feature extraction. Now, it's just a general term for methods of constructing combinations of the variable, right, to get around certain problems while describing the data with sufficient accuracy. So sometimes, just sometimes, data might come in a very raw form, and that raw form isn't so much conducive for your model. So then you need to either add more or pick up some entities from it. Okay. So you go into what we do as we call as data extraction. So feature extraction, sorry. Now in this case, what you are trying to do is to make sure that the variables that you have better describe your case study. So it can come in any form, right? It can be as raw as possible. Data sitting in its unique state doesn't necessarily have any case study to work with, or it doesn't necessarily fit to any problem unless you tune it to fit to the problem. Okay, exactly. So you put one or two together in order to be able to predict something. Imagine you're predicting identity, you need to combine one or two variables. I'll use variables from now on. One or two variables in order for you to get the right construct, okay, or construction or combination to be able to predict it. And these processes that you go through, you are basically extracting the features for your model. Okay, anyone has questions, you can unmute because I can't see the Zoom at this point. All right, then. Okay, another big term to use here, principal component analysis. So we are still on the data selection part, right? Yes, Anka Harrison, please ask questions. Yeah, I'm listening.
Please, is the feature extraction the same as feature engineering?
Not necessarily. You might confuse them, but not necessarily, right? Feature extraction, you are basically getting your data. So you've not, sorry, you've not even gotten to the part where you would generate very new data out of what you have yet. Do you get it? It's within the process, but no. So you are at the very forefront. Now, feature engineering, when you get to feature engineering, it means that you already have the variables that you know already. Okay, you know that these variables are what is good for my model. Now, the variables I'm having, they do not well describe or predict the model. You might already use it to predict the model and you realize that no, the accuracy is quite low. So what do? You make sure that for every feature that you have, you intuitively generate or engineer new features out of it. Okay. While they might be used interchangeably, they are not quite the same. One comes before the other. Okay. That's it. I hope that is explanatory enough.
Thank you. Yeah, I get it.
Yeah. Any other?
Yeah, so Michael, when you engineer the features, how are you able to validate whether that feature is relevant or it's not relevant?
How are you able to know whether that feature is relevant or not relevant?
Correct.
Yes. So we have in a data selection process, right? You can go ahead. One technique is to go ahead and build a model with all of those features that you have. Okay. And then we have a technique called finding the feature importance. All right, now you have your model. The model is saying that I have this accuracy. If the accuracy is good enough, you would notice that the feature importance there for every feature that you put in it, what is high and what is not high. Sometimes some features are inside for being inside sake, and they do not really need to, or they do not have very significant impact on the model's output. So we prune those features out, we take them out, and then we are left with the original features. You get it? That is one way. Another way is to also go the statistical approach. So statistics will also give you an example where you can use regression itself. So if you build a regression model, if your case study is regression, for instance, and you want features that best describe predicting your line, okay, you can go ahead and then build a regression, and then the gradient, this is smart. So the gradient in it, for every X that you put in it, it will have associated gradient. The gradient in it will tell you which one has a higher weight of predicting the output. So the ones with lower weights, you basically ignore them. You basically ignore them, or you remove them from your data set. All right.
All right.
Okay. So feature extraction, let it come at the forefront. You have your data. Now, before you work with it, you select the right columns out of it, then you proceed. Now, after selecting the right columns out of it, this is an optional process. Principal component analysis is an optional process. Now, this process comes on the fact that you basically, so some models, okay, this is very useful in when you are doing something we call as unsupervised approach, or models that are unsupervised in nature. So they do work well with lower dimensional data. Again, a big term. So lower dimension means that the data doesn't have lots of columns to work with. The columns are not too huge. Okay, so when we have a huge list of different features, and then we want to reduce it, we want to just shrink it down a bit to make sure that it's explainable, then that is when we go in for PCA. So it can look at 5 columns at a time and tell you that all these columns, I can shrink it down to 1 column. Then it will give you just 1 column. It does a very good job. It's an algorithm on its own. This process is an algorithm on its own. Now, this type of algorithm mostly is used as a step before you build your model itself. Okay, when you want to get the data in its small components, or principal, we call it principal components, just so you can build more like a model that learns from that smaller dimension. Again, technically, there are models that are very good on higher dimensional data. Also, there are models that are not quite good on higher dimensional data. Sometimes we do what we call as experimentation. You just throw everything at the models, and then if you're lucky and you get it right, you move forward. But if you want to really understand the individual models and how they work, with very good direction and understanding, you would know a model that doesn't require high dimensional data. And so you need to basically apply principal component analysis, or get your data into principal components and then feed it to the model, because it doesn't take that huge data. So this is also a step that you might want to consider in your pipeline. But like I said, sometimes most people, I tend to even ignore it most of the times, unless, of course, some cases where I'm doing unsupervised, it really, really works well in that setting. So you would not want to compromise this part. But sometimes too, you can simply go ahead, your model will work. If it doesn't work and you're trying different techniques, this is one technique to consider. Okay. All right, then. Okay. So the data preparation, we've talked about this, but of course, a very essential part is cleaning the data. Cleaning the data entails lots of things. There is not a one-size-fits-all in cleaning data. It comes from experience. Some data can be cleaned in a certain type of way. Other data, if you apply the approach you use for data X on data Y, you might get it wrong. Why? Because an example is removing missing values from a data. You can look at data in its raw form and then ask yourself, why is this particular data point missing? There could be a reason why it's missing. One, as an example, it could be the fact that the person is a ghost, it's basically a ghost record, so it shouldn't be there. So you can easily remove it. Another, it could be the fact that it's an actual identity, but the person doesn't have what do you call it? Some value there. Maybe you've taken details on some people, and then one person inside your list doesn't have a Ghana card. You don't necessarily need to remove that record from your database. A person is just missing a Ghana card, and there are reasons why he or she is missing a Ghana card. So you have to work with the data. Now you have to apply different processes to clean that data up. You can either impute or what do you call it? Fill in that value with a very reasonable value just to make the model learn that indeed there are people that will come, or there are certain data points that you're going to see that will not have Ghana card. So when this happens, then these people are what I call as other or something or unknown. You get it. So I'm simply trying to drive your mind to the fact that there is not a one size fits all as to how you can go about data cleaning. It's very, very unique or to every type of data set or the use case you're working with. So understand what you're doing very well. You don't rush the process. You never ever rush the process. You understand your data very well before you move to the next step. And the data understanding alone will help you to know what you are supposed to do in the cleaning step, what you are supposed to visualize, right? And then also what models you are supposed to choose as well. Okay, that was clear. So in developing the model, the exciting part. So what is the problem being solved here? And what is the goal of the model? The goal of the model will determine to what extent or to what degree that you would even consider as a good model. Okay, and also what type of error metrics that you would apply in order to minimize errors on the training data itself or minimize error during training, right? So every use case that you have in mind, once you bring up the use case, it will direct you. I think I missed something. I wanted to provide a chart. I have this chart, which will be a good guide. So it starts from the point where you ask your question, what am I building? So what I'm building is basically to predict credit scores. What type of data do I have? I have numerical data. And do I have history and the associated output? Right? So if you have history and associated output, it will take you to a branch. So that means you are considering supervised. Then you leave unsupervised and then semi-supervised or reinforcement learning somewhere. Then when we are on the supervised branch, you ask yourself this question. Your data, is it numerical or categorical? So your data is numerical in this sense because you're predicting credit scores, right? Or you are predicting, now this case study can be thought of in two ways. Either you are predicting whether the person is worthy of a credit or not, which will come as binary, yes or no, meaning let's give the person credit or let's not give the person credit. It can also come in the form of numerical value, where you predict the score of a person. Then later on the software side will decide on if the score is tolerable enough for us to give the person credit. Okay, so you look at your data. Now that data, if you look at what you are trying to predict, and it's basically your use case basically tells you, or your product manager tells you that let us know whether or not, then it means you are dealing with categorical. Then you branch to choosing a categorical model. If at the end, your product manager tells you, we have credit scores and it's in the form of numerical values. So when we give you details of a person, we want you to tell us their credit score. And that means he's pointing you to regression. Then you branch to the regression side and look for regression models. So on the regression side, there are models you can take from there. Okay. Since you are predicting regression, we have linear regression, so many other multiple linear regression, where you have KNN regressors, lots of regression models. Now, what type of model you will take can be experimental, but intuitively too, it will depend on the analysis you make on the data. If you make very good analysis on your data set, you might notice that sometimes if it's a linear relationship between your features and then what you are predicting, then you need a linear model in this case. But if you realize that you don't have very good relationship, okay, we are doing statistics here. If you realize that you don't have very good relationship between your input and then your output, and it is more like a scattered relationship, then it is a non-linear case study here. So even though you are going with a regression approach, but you are choosing a model that we call as non-parametric. If you have very good linear relationship or some correlation lies between your inputs and then your outputs, then you can go with the linear models. You can choose more like a lasso regression, a multiple linear regression. You can choose support vector machines with a linear mechanism, lots and lots of them.
Michael,
You experiment. Yes.
Michael, today's like the terms are hot, but so if you say linear regression, what are you saying?
Exactly. So I was just honestly, I'm just trying to do a brush through so that you will appreciate. But let's not
All right,
focus.
then what? I mean, if you have a plan, then what?
Yes. All right then. So if I say a linear regression, well, on the first note, what is a linear regression? It's one of those algorithms, right? It's an algorithm. It's an algorithm for solving a regression problem. It's one algorithm for solving a regression problem. We'll see all the algorithms for solving each one of those problems as we go forward. Okay. But we're just describing the use cases in this scenario. The Nobel's question come in. Now, what I talked about when I said a linear model is basically a model, right, whose relationship, okay, between its inputs, a model whose features has a very good linear relationship between what you're trying to predict. All right, how do I get you an example of? Now, we've all done some statistics, and then you know of yx is equal to mx plus c, which is more like an equation of a line. You understand? So an equation of a line has two variables to pay attention to before you get a linear relationship. It means that you have your x-axis, you have your y-axis, and the x-axis has some relationship with the y-axis. And this type of relationship is very linear, meaning that as s increases, y also increases. You understand? In such a case, it means we are dealing with linear regression in this case. And those type of models that are able to work well with that type of relationship are linear models. Okay, no better, was that clear? Exactly.
Because of the class. So if they are fine, can go ahead.
You have questions?
I asked a question because of the class. So if they are okay, then go ahead.
Yeah, I'm asking if anyone has question again. I see someone in the chat. Okay. All right. Questions? Don't get lost. We are basically introducing the processes. Okay. Now, right after this, I'll walk you through what data processing looks like in real life. But this is just an introduction of the processes that is involved before you arrive at a model. That is why the big jargons are coming through. Right. Okay. So on the other bit, that is the nonlinear model approach. So I explained linear to be basically where we have features and then targets getting a very linear relationship. Okay, as one feature increases, yeah, the output also increases as well. So an example is you growing up. As time goes, you grow up. As time is moving forward, you don't grow down, okay, or you don't turn to something else that is not linear. The more time goes forward, the more the years go by, the more you grow. That is a linear relationship. Non-linear relationship comes in when the X is not directly influencing the Y in a linear approach. So it's not that when X increases, Y increases. No, then it becomes a non-linear model. Now, those ones, if you've done CS, and all of you probably, I'm going to assume that, then those ones, an example can be more like an exponential function, a trigonometric function, a power or something. Okay, they are non-linear. But if you have y is mx plus c, directly will give you a linear relationship each time you plug in your variables. But if you have an exponential function, it never gives you a linear relationship. So you can basically try and experiment and see what I'm talking about. I think graphically, it makes sense doing it graphically than saying it out loud, right? So once you get these models, right, pay attention. So we are still on the processes to develop a model. Once you get to understand your relationship and you decide to choose one type of model, there are some things that you need to pay attention to. So you build a model and now you have to make sure the model works for your use case. A model will work for your use case if it is free from overfitting, okay, or if it is free from bias. Okay. Now, what is overfitting? Overfitting basically happens when you build a model and then you test the model. The model works, but when you show it new data, it doesn't actually work like that. Okay, it captures noise along with the underlying pattern in the data. So it doesn't work as you expect. And in that case, it means you've not really built a model that much, right? The model is closely fitting to your training data alone. So you have model that can only work for what you trained it on, and it doesn't work well in real life. Let me give you an example of what this is in real life. Imagine you sit in a class and your lecturer teaches you something. So you are taught 1 plus 1 is 2, 2 plus 2 is 4. You understand that very well, but when you get to exam, when a different type of question, more like 6 plus 5 is given to you, you're not able to answer. It means your brain has overfitted on what you were taught in class, and you didn't really see different examples for you to adapt to the 6 plus 5. And that is why you are failing. So that is overfitting as an example. You understand? That is overfitting. So this term is thrown around a lot in the machine learning ecosystem. So I'd want you to understand it from here. It's theoretical. You have questions? Are you with me?
Yeah.
Yes, sir.
Okay. All right then. So when we are dealing with bias, it means we are underfitting, overfitting, underfitting. Underfitting, so we said overfitting means you've learned the thing very well in class, but then when you are shown new data, you're not able to work well. Underfitting is when you are not able to even learn what is happening in class that much. So your score is very low. In that case, also, when you see new data, you are not able to, perform very well on it because you didn't see different examples in class for you to really, really understand or capture the complexity of the use case very well. So you don't understand it well. Now that is underfitting. And in this case, you would want to avoid that. So both cases are what you should try and avoid. You should try and avoid overfitting. You should try and avoid bias. Do that. Get a model that actually understands your training data and is correctly able to correctly able to predict something when you give it new data. So before you even say that you have a quality model, we do test the model. So aside training data, there is also what we call as testing data. And sometimes we go a step further and do what we call as validation with a validation data. You get it? So training data, fine, the model worked well. When you tested it, you did realize that you had 80%. You go a step further to validate. What is the validation saying? The validation is saying that you still have 80% or you have close to 80%, more like 79, it's tolerable. Then you have a quality model. Else, you don't actually have a quality model. Now, this is a bit complex. This is what it would look like if you are overfitting a particular use case. So you don't actually learn, but then, yeah, I think I would use this word. It's more like when you do Chiampo or Baba, you understand. So you don't actually learn from the problem you are trying to solve, but then the examples you see in class is exactly what your mind is tuned to. So you don't understand the problem very well and why the problem is solved in that way. But when you are given the question, you try to memorize the processes that the lecturer went through to arrive at the answer. And so you write the same thing until you arrive at the answer. And that is what it's doing here. So there is actually a linear relationship here. It can't find a linear relationship, or there is a type of relationship here, not necessarily linear. But then because it's overfitting, it tries to pass or get each one of its answers following certain patterns that it has in memory. Okay, and in that case, it becomes more like a complex model. So those type of models are very complex and they work only well with the training data. So if you show them new data and it is lying at a certain pattern that is not quite the pattern they've memorized with the training data, they are not able to work well. Okay, that is what happens. A better example is the class example I give. Now, underfitting in this case is also the fact that it has established a very good relationship here, which it assumed to be linear. That is quite good to some extent, though. The reason is that it's still having different parameters that are, or values that are lying outside of the line. So the line was good, but the line was not good enough. It's not actually a good representation of the data. Okay, so it's underfit. If you take a closer look, I think we won't do that here, but if you take a closer look, it was able to get 1, 2, at least 3, 4 correct. And there are a lot of other examples that I didn't get correct. So those that I didn't get correct, you do the ratio of what it got right against what it didn't get right, and then, or against the total data, and then you realize that it's not performing quite well. So that is underfitting in this case. A very good model is a model that can get a balanced fit. So between this and this, it's not necessarily a straight line, and it's not necessarily a very rough line that is trying to learn everything, but it tries to follow the pattern a bit. So the pattern lies this way. So following the pattern closely a bit, it's able to capture more. You understand? So this captures more, this is closer to being better than this is closer to being better. And so this is what a good model looks like. You understand? Questions? I think you should think through from here and then ask questions. Okay.
Do you have a place to go with this?
Yes,
Hello.
yes, go ahead.
Yeah, please, how do you know whether it's overfitting or underfitting?
That is a very good question. It's in the slide somewhere, but I'll talk about it now very briefly, and then we can look at it better when we get there. All right, next question. Anyone else?
So how will a model overfit? Like, what will cause a model to overfit?
Okay. That's also very good.
And then I also want to ask that does overfitting affect the precision and then accuracy of the model? Maybe if the model is able to predict well with the data that it has already seen before, will it increase the accuracy and all those precision something, or like it will calm down? I don't know.
Okay. So you're asking if overfitting increases the accuracy, because you see that it tries to imitate each one of those lines, right? Okay, good. Okay, anyone else? All right. So first question. First question is how will you know? Yes, how will you know if a model is overfitted? Now, this is quite an experimental approach. Okay, so the ML ecosystem will tell you that there isn't any specific match for you to know if it's overfitting, but then we have something we use to test, and it has been accepted by the entire community, and that is you having to, we say that the accuracy on your test data or validation data shouldn't be so different from your accuracy that you are getting from your training data. So you can build a model, you build a model, you first test the accuracy on the training data. Training data is what it has seen before. So how well did the model perform on data it has already seen? You get an accuracy of 90%. Okay. Then how well did the model perform on data it hasn't seen? That is what you hold out, the test data. Test data is what you don't show to the model. So then you compare. Your test data is giving you 80%, and then your training data is giving you 90%. Difference of 10, there is a problem. Yeah, sometimes difference of 20, there is a problem. You go ahead to also run your validation, and you realize that your validation is giving you 70%. There is a big problem. So it means that your model is working very well on your training data, but it's not working well on validation and test data. It is overfitting. It is learning very well on the training data. It's not able to adapt to the real world conditions. Mind you, that the real world condition is actually the test data. Okay, you get large samples of data, and then you take some out, you keep it somewhere for your testing, and then you get a sample or a large size for your training. You train the model, it understands what you showed it. All right. So put yourself in the class example. Your teacher tells you something or teaches you something. You understand it from the class, and then you are able to give answers. So he gives you different questions, right? Teaches you that same question in class, and then asks you, cleans the board, and then tells you that this is the question that I taught you. Now give me the answers. Of course, everyone here will get it right. Because I mean, you've already taught us this in class, and then right on spot, you're asking me what they are. Then I'll give you the answers. Without even knowing the processes, I can tell you number one is 3, number 2 is this, give you the answers. And then some of them, I might either fail or not even fail anyone at all. But how well I'm able to remember that is the accuracy of the training data. How well I'm able to remember what you taught me is the accuracy on the training data. Now you come to exam, and then they give you different questions, different from what you saw in the classroom. And now that one, you're not getting it right. So you get 70%. But then in class, you're able to remember or to more like a 99% accuracy. So you got 99 out of 100 correct in class on the data that you were taught with. But then when you came to exam, you were not able to get that right. So you got 70% or you got more like 60%. You're overfitting there. So it means you didn't really understand what was taught in class for you to adapt to different use cases. That is overfitting. That is how you determine that it's overfitting. So the difference between your exam score and then the score you get in class with what you learned, what was used to teach you shouldn't be so large. It should be considerable. Most of the times we say that it should be very close. If it's very close, you got it. Sometimes it's very rare for your test data to be better than your training data, but if you get it that way, you are perfect and the accuracy is good, then you thank your God. But most of the time, from my experience, it doesn't happen that way. Sometimes your training data will be higher than your test data, but it should be very small, more like 80 against 78, or 80 against 79, 80 against the worst you can do, 75. Don't go too much. And even that, you still need to look at the model too. So it's like you trust it, but you don't trust it that much. Okay, then that is when validation also comes to help you in the line. Now, the next question is, what's the next question? What causes a model to overfit? If the training data size, one, there are a lot of things that will cause a model to overfit. Now, a very essential part is if the training data size is too small, or probably it does not contain enough data samples to accurately represent all the possible inputs data values. Okay, it doesn't contain enough data samples. So you can, oh my God, this guy. So you can build a model, all right, with some data points, but then you don't really have enough features or enough samples in the data that are varying for you to do well on real life data. Again, I'm going to the classroom. You get to see 1 + 1. You get to see 1 + 2. He never showed you 2 × 3. And so you don't know multiplication, but then you know addition. All right. So in exam, when you see the multiplication, you are shaking, you're not able to answer it correctly. So it means that if multiplication was showed to you in the classroom, you would have been able to get it right. So your data samples doesn't vary that much. Please give me a minute. Do you understand it?
Yes, sir.
So that
Yes,
was
sir.
clear. All right, then. Let me take 1 minute. I'll be back. Okay. All right. Yeah. So I believe that should answer your question. I think the last question now was if it's a good model, if an overfitted model is a good model. No, it's not actually a good model. It can only be a good model to your training data. It can't be a good model to the real world data. The real world is what is important. Okay, your test data or your validation data represents what your model hasn't seen before. So if it's not performing on test or validation, it means it's not a model. It's not a good model yet. You need to work on it. Understand? get enough variance in the data or something, get more data. Okay, enough variance actually solves it. So get enough variance in the data just so variations in the data just so it can adapt to the test data. Okay, so how it looks like. So when data is low variance, right? Low variance or low bias, you can see that all of them are cluttered in one place, of course. So you don't get enough samples distributed about for it to, learn pretty well. So high variance also, you can see that the data is spread across. So in this case, you do get different use cases or different insight into what can possibly happen in the real life. Now look at high bias. It's deviating so much or getting very much away from the green spot. And so that is high bias, and then low variance is deviating so much from the green spots. And so that is not quite ideal. You might want this one in this case. You understand? All right, it's quite technical here, so I don't want to go that deep. You will see it as we build a model to represent each one of them. It's not ideal though, but we have to know how each one of them behave in that sense. So what is the general rule for building a quality model? A quality model is basically a model that have minimum error on the training data, yes, and also minimum error on the test data. So errors on the training data shouldn't be that much. That is good. But then its associated error on the test data too should coincide, they should align. Now, if the error is also big on the training data, that is fine. But if you test it on the test data, it should be quite good. That means it has generalized well to the real world conditions. Whatever the case may be, your test data shouldn't lie so much away from your test data and your training data's accuracy. And that is when you have a good model. Okay, so that's the general rule. Test data accuracy is okay. Whatever it comes out, fine. But then your training data accuracy is okay. Training data in that sense, accuracy is okay. But then whatever comes out of it shouldn't be better than your test data. If it's better than your test, you go on to validate and it's better than your validation, then you have a problem. You need to correct that. Okay, because real world is actually what your model hasn't seen. So that's the general rule. All right, then. Okay, so rule of thumb to developing a model. Now, the best you can do is to keep it simple. Okay, there are so many complicated ways of doing the same thing, right? But sometimes just a normal model or a single model might even work for your use case than building an entire ensemble or entire stack of models. An ensemble is also an approach that we use to build complicated models if the data is very complicated to work with. If the data is very complicated to work with, there are approaches or different mechanisms to architect the model development. Okay, it's more like this place, it looks more like you are architecting group of models in order for them to have unified power to operate. Okay, so in that sense, those type of models are called ensembles. But you would want to first test out how a single model works on the data to see. Sometimes an ensemble may not necessarily be important or not necessarily be what you want, so it's not that needed. Okay, if the single model works, it's lightweight, it's simple, it's explainable. A very important thing. If you can explain it, it's better than what you can't explain. Okay, exactly. Now, how you also get very good accuracy, so how you try to minimize overfitting on what we have discussed so far is by choosing a technique called cross-validation. Okay, we will look at it, but in this case, you have lots and lots of different pieces of test data and you pick them randomly at a specific point in time. So you hold out certain portions of your data and then you iterate through your data set as you go ahead. So different portions of the data are used to train and then validate and then see the accuracy. Then you go to the next iteration and then you train and validate. So we will go through all of these processes to see, but then know that it's one approach of testing that a model is not overfitting at all. The accuracy you get here will quite say the truth because it has worked on lots of different training and then lots of different testing. For linear models too, there is also some models that do help with minimizing overfitting. One model is lasso regression. Another model that you might want to look at is range regression. I don't think I put it here, but those models have what we call as regularization. Another big term, we'll look at that. But then understand that linear models may have the problem of overfitting. And then one approach to minimize the overfitting in these type of models is by regularizing them. And there are some models that have regularization out of the box, and one is the lasso regression model. Okay. All right, then. Also important. So interpreting the results. Okay, this should be the last in this case. We are 7. So I show you a notebook that is very interesting. So once you are done, of course, once you are done validating your data, you go through the cross-validation, you do your test, and then you make sure that you get everything right. The results of the model, like what you predicted, has to be explainable. Okay, so once the test set has been used, you must find new data, and then work with the data or send the data to the model and see the results you are getting. And make sure that you understand the results you are getting very well. A good model is as good as your understanding of its output. If you don't understand its output so much, well, these days it's happening though, because the age we are in, some models are very black box to us, so we have exceptions to that. But a typical machine learning type of model should be a model that is explainable enough. Means you understand very well what the output that is given is and why it comes out that way. Okay, and there are packages. There are lots of different packages or libraries that help us with interpreting the results of the output. So that is also quite easy now. But at first, it was quite a tedious process. Okay, then, before we move on to the next session, anyone else with a question? The overview is okay. Okay, so you don't actually have to be so bothered because you've not done anything related to ML itself. It's just the processes we are discussing. It's a discussion of what is involved in building an ML model, right? It's charged up. Right. So what's your understanding of it? Questions? Okay, then I believe we are good. All right, so I have a little something for you. Okay, so yeah, what we have here is, okay, this is something I did some time ago. I don't remember which year specifically, but I had it around and I wanted to show you. We will not get to the ML part of it, but it's basically a Jupyter notebook, right? Or in this case, converted to an HTML. What is in here is the approach I took to answer certain questions. And this particular project was about investigating a data set to understand why certain, appointments are missed by patients in a hospital. So I think it was in Spain. And then that hospital, each time that appointments are booked by individuals in the hospital, they tend to miss their appointment. And then we have to answer the question as to why they missed their appointment. So what I'm going to do is to basically do a walkthrough so you understand the processes that is involved in unraveling some insight from the data, even before you get to machine learning. Even before you get to machine learning, what are you supposed to do? So we mentioned in the presentation that there is this thing called data wrangling. There is something you must do to understand your data very well before you can, extract the relevant features out of it. And that is what we call as EDA, or exploratory data analysis. So most of this actually has processes that I went through to better understand the data first before moving on. Now, this data is available on the open internet, so I guess we can all have a grasp of it, but I'll post this one in the group so we all see it. So first of all, we talked about asking questions and then trying to solve questions. Okay. In this particular presentation, try and ask questions as much as possible. And I'll urge you to focus less on the code and then follow the story. Okay, the story is what is important. So we ask questions for analysis. I decided to ask questions. So what questions am I asking? That what is the percentage of patients who show up for appointment versus patients who do not? All right, based on what I had from the case study, this is the first question that came to mind. 2, on which day is it likely for patients to miss their appointment? 3, does the month within which the appointment was booked have any significant impact on whether or not patients will show up for their appointment? That's a deep question. So I want to understand if the month has something to do. You know, some months have lots of holidays in it. Or is it that there are some holidays on certain occasions that patients are not showing up? You never know. So I just want to understand. Now, does the patient's age determine whether or not he or she will show up for appointments? Old people, if they don't get help, they are not showing up because, I mean, he can't get out from his wheelchair to come to your appointment. Or probably the time you set for him, he's not getting the help as at that time. So that could also be a factor. Ask questions as much as possible to understand the data you are dealing with. And the last one, how does the patient's gender associate with attending appointment? Is it that males are attending appointment better than females? If that is the case, then why? Do you get it? So at the first start of the whole process, I decided to ask questions or state the questions that are bothering me and then try and answer the questions. So the entire Jupyter notebook does analysis in order to answer all these 5 questions. And that is what we'll go through. So here we load our data, of course, which is not quite important. Then we look at the data itself. So what I did is, at the first stage is the data wrangling. And in this case, I'm inspecting the data. So what data do we have? We do have 110,527 samples. Okay. And each of these samples, we don't have any null values. Remember that I talked about data cleaning. I talked about data cleaning, and I said that you need to look out for when you have missing values in your data. Missing values need to be treated. You have to understand whether they are actually missing or there are reasons to why they are missing. All right. So in this case, it wasn't a bother because we had no missing value. And so my understanding of it was okay, then that's fine. So this code is basically also checking how many missing values we have in each of the column, right? These are the columns. So you realize that this column, this column, this column, and then we have no show here. In a typical machine learning setting, I've talked about features in the other presentation. So what are features? This is what represents a feature. All these, patient ID, appointment ID, gender, the IDs, normally we don't treat them, but let me add them for this case, okay, on a high level. Schedule day, appointment day, age, all these are features. Now, what you are trying to predict out of the data you have here is your Y. And that one is not part of the features. It's your Y, or what we technically call as the target. So what is a target in this place, right? Because we are dealing with no-show appointment, and then we have a column here that determines whether this particular identity, this patient with this appointment showed up or not. And in this case, they didn't show up, so it's no. This can be treated as a target for us to predict whether a person will show up or not. So the no-show here becomes our target, or our Y, or what we are trying to predict. And the rest of what we have here are our features. Do you get me? So we have how many features here in this case? If I come here and I look at no-show, from 0 to 13, it means we have 14 data, we have 14 columns, right? Now, out of 14 columns,
Guys, please speak and ask questions. I'm begging you. This is very important.
yeah,
Speak and ask questions. If you are confused, talk about it, please.
yes. So this is your target, and then these are your features. Okay, so we have 13 features. It starts from 0. So if I say 13, it starts from 0 to 12. So then we have 13, right? Exactly. And this very one, which is the no-show, will be your target, or what you are trying to predict in a machine learning context. All right, questions? this knowledge alone is very heavy. So if you understand it, I'll be very glad. All right, are we good? Okay, so I actually went through 3 processes just to be very sure that my data has no null values. All right, Bernard, go on. Ask.
Please, how do I say it? The info part, the dot info. After knowing all those parameters, how can it help us to build a better model?
How can it help you? After knowing all these parameters, how can it help you to build a better model? I think that
Yes,
question should have been asked even before you get to build it. I'm sorry, bringing the data here. So knowing what features to take is the first step in the process. Okay. You have to know that this feature actually has something to do with no-show. All right. So speaking very emphatically in this context, you would notice that we have gender of a person. Now I asked the question, how does the patient gender associate with attending appointment? That's because intuitively I know that there is a possibility that gender can affect a person showing or not showing. I'll give you an example, which, I mean, pardon me for that, but imagine putting an appointment on a D-Day for a female who would, of course, they choose the appointment themselves, but does not know that they'll be flowing on a very particular day, right? It gets to that part and then that day, sorry, and then there are cramps and then she's not able to make the appointment. A man would have made that appointment. You understand? So in my mind, I know that that is a factor. And so gender has a role to play in predicting whether a person will show up or not. And that is how you think through the problem to gradually pick out the relevant features to predict your target. You understand? So the questions you ask here are the same questions that end up bringing the features, and then you also explore them, basically, or the questions you ask forefront. You get it?
thank you.
Okay, let's move forward. It will be clearer as we go forward. More questions? Okay, sure. All right then. So at this point, I know that there is nothing missing in my data. Here too, you can see that there is nothing missing in my data. It's a visualization. It may not be clear to you, but it's basically trying to, if there are missing values, you would have seen some marks in it showing that data is missing to what degree, but there are no missing data. So I said, this is what I made out of the data validation process or the data quality check process. The data set contains 110,527 rows. Yes, Amponsa. Yeah, go ahead.
Please, if I want to understand, so without all the features, then we have the targets. Can we still work on the model?
Yes, you have features, and then you have a target. Yes, so
Yeah.
it means you have complete data to work on a model.
Oh, okay. But you are saying we are dealing with the target. That say the target is very important.
Very, very important.
Okay, so that's what we are really working it or looking at.
So you are working with
The target
features and target. That is what is important. Your features are what determine your target. Right?
Okay. So
Features
I
are
was
what determine.
thinking without the features and we have the targets, we can still work with the model.
No, it's impossible.
I think you should listen to it well.
Okay.
Maybe ask your question again.
Okay. Okay. I was asking if without the features, I mean, we are looking at the target is what we are looking at. We work on the model. So I'm asking without the features, can we still work on the model once we have the targets?
No. Okay, let me show you something. It's a no, but let me show you something. So x plus y, or let's say x1 plus x2, right? Plus x3 is equal to y. This is your target. This is your feature. This is your feature. This is your feature. All right. Sorry about that. Okay. So I'll show you something before the network interrupted. That this is your feature. This is a feature, right? Feature 1, feature 2, feature 3. And this is what you're trying to predict. Before you get Y, this is a very basic example in terms of mathematical sense. Before you get Y, is dependent on these three. Okay. So these three are chosen because you understand that they are what contribute to getting Y. If they are not there, Y is also not there. You can't predict Y when you have nothing at all to predict with. So at least you should get a feature, one, even one, and then you feel like it has some connection with Y, you'll be able to get a model. So without features, you can't get a model, you can't predict on Y. Do you understand? Was that clear?
Okay, so does it mean that based on the feature, we'll just give you the target? I mean, without, if you have a target, even the features will actually give you.
Come again.
I'm saying that.
Yeah.
Does it mean that based on the if you have a target, maybe a particular target that you want from a certain data, so that means based on the criteria or features will actually give you the target. If I is that what you are saying?
You've asked the right question, and the answer is yes. Based on the features, that is when you get a target. So an example is the human being example I gave. Based on the qualities of the human being, that is the features of the human being, you'll be able to tell their identity, right? So it's very important there. It's very important. If I ask any of you right now to, if I ask any of you who is in Ghana here, and then it's part of the governmental body, it's very short, right? Has bowed head, very, very short, has bowed head, normally wears suit. He speaks in front of a microphone with pulpit in front of him. All of you, your mind will start tuning to Akufo-Addo. Akufo-Addo is, the name Akufo-Addo is what you're trying to predict. But look at the processes I went through to describe him. All of those things that I said are features. All of those things that I said are features. So that is how it works. You understand? Is it clear from here?
Hello?
Are you with me? Okay, then. So we can now profile our data. Is anyone asking a question?
Yes, please.
Yeah, please go ahead.
Please, to start tackling the problem itself, are you supposed to ask those question analysis by yourself to be able to generate those features and the targets?
Yes,
based on the question analysis.
You're supposed to. Okay, be careful with this one. This one is when you've already gotten your data, right? But there is one process called, you have to state the problem, or you have to get the problem statement written. The problem statement is when you know that there is a problem and then you want to solve the problem. So in this case, the problem here is actually the fact that patients are not showing up for appointments. So we want to determine whether or not a patient will show up for appointment. That is the problem. So once you understand the problem, you listen to it and you understand it in this sense, then you begin to think, what could make a person not attend meeting, right? So then you go ahead. The person's gender could affect the person. So that's when I give an example that it can be a female or a male reasons because of the differences between, gender. It can be the fact that the person is old, so old people do not attend meetings. It can also be the fact that maybe the person did not get an alert. Pay attention to the way I'm deducing the features out of it. It can also be the fact that after booking the appointment, they didn't send them an email at all. And so they don't even see anything to refer to. Or we did send an email on the first appointment book date, but then we didn't consistently remind them. So we didn't send reminders. So the question is, did we send reminders? And that alone is also a feature to describe whether a person will show up for appointment or not. So I ask all these questions forefront just to get down my feature. So each question I ask has to correlate to a feature that I'll pick. If I ask a question that is the gender affecting they attending or not, then I have to get a feature called gender. Is the fact that we don't send them alerts affecting it or not, then I have to get a feature called SMS received. So did they receive SMS or not? Okay. Now, is the person sick to the extent that they can't help themselves? Are they handicapped? Do you think that they need help before they can come, and because they didn't get help, they didn't show up? Could that be the reason? Then we get a feature called handicap. You see the way it's coming? Now, is the person an alcoholic person? Do you think that it's because they drank on that very day that they were supposed to come? Probably a day before that they drank and then they slept and the time passed away, and that is the reason why they didn't show up. And so you bring a feature here, so depicting whether the person is an alcoholic person or not. Do you get it?
Yeah.
So it boils down 1 until you get features that best describe what you are trying to predict. So each question I ask, I tend to bring the no-show, whether they show up to appointment or not. So I ask a question if they are male or female, and I say that, is the gender a factor that could make them attend or not attend? When I say attend or not attend, then I'm pointing to our target. When I say that, did they receive an SMS prompting them that they should come? And because they didn't receive, do you think that is the reason why they attended or they didn't attend? And I brought SMS here and I'm pointing it to no show. So everything points to the target. We've gotten quite deep. I think they should let you understand to this extent, but I'm glad that we had to go this deep. Do you get me? It's very, very important that you understand why features are there and how they relate to the target. It's very important. If the features have no relationship with the target, it doesn't really say anything. It can't predict very well. And that is why we go ahead to explore the data to make sure that we see some story behind each of these features and then the targets as well. Does that answer you?
So I want to play it out right now.
Yeah.
So based on the question you ask,
questions like this. All right, I'm listening.
Yeah, based on the question you ask yourself, that's when we were able to get the features, then able to get our targets.
Based on the problem statement. Yeah.
All right.
Exactly.
Thank you very much.
You're welcome. Any other? Okay. So the problem we want to solve, what we want to solve is the target. And how we are going to solve it is by using the features. You understand? Great. So the summary info checks for NAN's report that there are 0 amount of null values in the data set. We didn't get any null values. So it means that all of the data we had, it's clean to some extent. So no empty value. That's what it basically means. You go ahead to inspect it again. So we check the unique in the neighborhood column. So neighborhood is basically describing where they live, right? So we see that we have how many here? I didn't do a count of it though, but if you come here, let me see. Okay, there should have been a describe somewhere. Forgive me for that. Yeah, but we have this represents all the unique neighborhoods that are found in our data set. Okay. So then we look at the appointment days, just 5 rows of them or 5 slices of them. Appointment day. Let's go on to what's important. So answering the role question. So in this place and in this very session, you would realize that I'm trying to do anything possible to get a peek of the data. So patient ID unique, I realize that we have 62,299. Now this is questionable because original data, listen to this story. Sorry. Originally, we have 110,527 samples in our data set. Patient ID is also this number. But unique number of patients that we have is 62,299. What do you think is happening here? Anyone understands this and can contribute? What do you think is happening here?
Maybe there are some duplicates.
It means there are some duplicates. Thank you. It means there are duplicates. And why are they duplicates? It means that some people are booking appointments, more than one. You get it? So look at the appointment ID to back the statement I just made. Appointment ID is very unique. So you can book appointments more than one, but then the appointment ID is very unique. So you can book 2 appointments for 1 patient. So we have duplicates in our data. Some patients are booking appointments more than one. And that is something you also have to take into consideration. Why are the patients booking appointments more than one? The moment you find this one out, you can now begin to answer that question. Why? Then you explore. It's a beautiful story. Now, okay. So I said patient ID and appointment ID columns have 62,000, blah, blah, and 11,000. I meant 110,000 unique samples respectively. Patient ID and appointment ID have very unique rows. However, unlike patient ID, appointment ID columns contain 0 repeating categories. Hence, it's very unique and sample specific. And as such, will not be considered for analysis. So we didn't consider appointment ID for analysis. I think here I didn't even state the real reason very well, but as you grow, that is when you get experience. It should have rather stated the fact that more patients are booking appointments repeatedly, okay? That is what was important in that conclusion over there. Now, again, we go ahead and then we check for duplicates in appointments. Of course, still, appointment ID is getting some duplicates. Okay, which is quite surprising. So a better solution would be to set it as an index of the column. So I have to set this one as an index. All right, this very area of the process is basically trying to unravel the nitty-gritty of the data itself. So you've not even gotten to where you would clean the data, but you are looking at the data itself in its raw form, and then how some things are done and what you should do to it in the next step. So it's basically checking the structure or the quality of the data in this case, you understand? So moving on to the data cleaning step, what happened in data cleaning? Now we don't have null values. All rows are very much filled, and so we don't have nothing to do there with imputation. That is filling in null values or whatsoever. So we didn't do that. Now, the very important thing we did here is to try and drop all duplicates as much as possible, which in a typical scenario, you should try and investigate first before you attempt to drop duplicate. Okay. Now I just renamed this column from no show to show, no show with a dash to no show, just to make sure that I can easily access it, because writing the dash was a pain. So this is code specific and nothing serious. But then the very beautiful part is when you create a report of the data. So the report is going to tell us that number of variables that we have is 14. Indeed, number of observations is this after I drop the duplicate. Now we are having 3 numerical columns and then 8 categorical columns, making a total of making a total of 8 plus 3, 11. And we have 2 datetime columns as well, and then 1 Boolean column. So in all, we have 14 columns. Now, because there are no duplicates and it has been dropped, we have 0 duplicates as well. So all these analysis, you get it. The profile report is now making you understand the raw data's form very well. So appointment ID is basically an ID field, so there's nothing to learn from there. But then let's look at gender. So gender here has 2 values. So there's an example of a categorical variable. So you get it. Now this puts down here that it is what? Categorical. This is what I've been trying to explain all this while. That data of this form, where you have distinct values, right, are what we call as categorical. So gender is categorical. And gender being categorical, it means that it has values in there that we are certain that are definite. And in this case, we have female and male. Now, male samples are 38,485, and then female samples are there. So we have more females than males, which intuitively could also draw my attention to something that one of my questions should actually be looked at. The fact that gender has a role to play in predicting no-show, because the females here are a lot. See, the females are a lot. Now the scheduled day, the day of schedule is also visualized here. Then we have 103,000 distinct dates to look at. That is a huge number, so lots of days, but this visualization isn't clear. You can see that there are certain peak days. There are days that go high a bit in the graph, which we'll also look at that very well. Then we have gender too. Distinct wise, we have 104 distinct, age values. So that is how wide our age range is, from 0 to almost 100. I'm not sure it gets to 100 very well, but we are looking at about 80 something to 90 something. So it means we have old age in it. And if you look at the distribution, babies tend to be a lot. So you see the babies, they are a lot more than whatever we have here. Then people from far above 50 to 70 to 60 thereabout, I can look at it, it's like 60 something. Yeah, but a better visualization is down. Are also quite a lot, so it's in. Now this will just show you an overview of what we are looking at. If you come to the neighborhood, apart from the one which is very determined here, that is the Jardim, this particular neighborhood, lots of people are from there, followed by this, so it's in order of 5, right? We have lots of people coming from here. Then other ones that are very minute in their representation, you just put them together and then name them as order. So 76 orders, but the neighborhood that we have represented a lot is this particular neighborhood. Do you get it? So that is the very summary of the analysis right there. Then we go deeper into what we can do manually by ourselves, the exploratory data analysis. So because we are dealing with hospital, of course, this is just a small little thing for you to get excited about the processes. So what are we answering in this case? Research question 1 is asking the question, what is the percentage of patients who show up for appointment versus patients who do not show up? Okay, now this graph or this pie chart, this is what we call as a pie chart, is saying that for all the percentage of patients who show up versus percentage of patients who do not show up, we have 79.9% of patients not showing up, and then we have 20.1% of patients showing up. Quite interesting, which means that the points that our superiors were making are valid. It means that truly a larger number of the patients are not showing up, and it's up to almost 80% of the times that we ask patients to show up. Which is quite interesting. So it's problematic. So we have a problem. Now, we go ahead to say that out of all those that don't show up, right, representing 0 with, what does 0 represent? Yeah, I think no show, and 1 representing show. We have 97% of people that are alcoholic, not showing up, and 3% are showing up. Okay. Wait a minute, let me get the visualizations example. I didn't put any head in here. Okay, I think I'll take that again. Right, so what we do have here is actually a distribution of the categories we have. So how many data points in our data represent people that are alcoholic? That's what we are doing. So 97% are alcoholic, 3% are non-alcoholic. And then people that have hypertension, 80% of them have hypertension, 19.7% do not have hypertension, 92.8% have diabetes, 7.2% do not have diabetes. Okay, so what I wrote here is that we have 97% of the patients in our sample data addicted to alcohol. 97%. And do you think an alcoholic person will tend to show up for your appointment? Now, that is a question to also ask. If you go to SMS received and the others, we also understand that 67.7% of the people received SMS, indicating that they have an interview to attend, but 32.3% did not receive an SMS. Okay, now we also have 90.2% of the data sample indicating that there are people on scholarship. Interesting. And then 9.8% are not on scholarship. Now we have 65% female and we have 35% male in our data set. Females are a lot than males. Then the question 2 that we are trying to answer, on which day is it likely for patients to miss their appointment? See, as we go down the exploration, we are answering each question as they come through. So on which day? So we have days visualized there, and which days are a lot. So the second day of the month is when we tend to have lots of appointments. Okay. So the day that we don't have a lot of appointments at all is on the 29th day of the month, not a single month. It's actually spanned from lots of months. So it's an aggregation of lots of months. So on the 2nd of every month, looks like we have very large and significant 2nd, 6th, and then 3rd. We have significant amount of appointments on these days. So we have more appointments coming through on 2nd, 3rd, and 6th day of every month. You get it? Then day of appointment versus attendance. So here you can tell the story that on the 2nd of every month, we do have lots of appointments, but then the absenteeism and then the presence. So what you see in red, what you see in blue is being present. Okay, so most people are present on the 2nd. And most people too are absent. Well, it tallies because we have lots of people having appointments on these days. But what is important is that we have lots of people showing up compared to a lot of people that are absent. Now pay attention to what we have on 8th, 1st, 30th, and then 7th, or even this one. Absent. So on 30th, on 8th, for instance, we have lots of people missing appointments and very few people, or significantly few people, actually attending the appointment. So red is actually higher than what's in here. You get it? So people are missing appointment on 8th, missing appointment on 1st, 30th, and 7th. So the conclusion, a greater number of patients who booked appointments on 1st, 7th, 8th, and 30th day of the month failed to show up for the appointment. Why? So you have to go down to answer that question. But then we are still not done with the research questions we stated. Now we go ahead to ask, does the month within which the appointment was booked have any significant impact on whether or not the patient will show up for the appointment? And how do we answer that? Oh, I'm sorry, the graph didn't come here. I think the graph wasn't, I didn't run this code, but then I think the solution now is that there is little to no association between the month of appointment and appointment absenteeism. So the month of appointment, the month within which the appointment was booked, doesn't actually have anything to do with whether they will attend or not. So you do realize that for the first time, we found a feature that doesn't really correlate or have anything to do with what we are trying to predict, which is the target. You get it? So it means that, Norbert, your question as to whether to determine if a feature is good for a model or not, this is one way. So the exploration now tells me that the month it's not that relevant. So it means that it's not a feature that we need to pay attention to. We can simply plug it out of the features. All right. So if you think that the month has anything to do with they showing up or not, that is not true. That is what this is telling us. You understand? Our time is up, but do I have like 5 minutes? Yeah, this guy. All right, then. Let me take like 5 minutes.
Yes, sir. Yes, sir. You have 5 minutes.
All right. So the next question is, does the patient's age determine whether or not he or she will show up for appointment? So patient's age, the age of a person. Now I ask this question because I think that old people who may not necessarily have the help that they need may not show up for the appointment, which is very significant. So here we tend to try and answer that question. Oh my God, I think I'll rather come here so I can run the code. We are missing some visualizations. Okay, I missed the visualization there. I'll try and run it again and send it to the group. The distribution of age column is positively skewed. The tail is larger towards the right-hand side of the distribution with a skew of 0.12. Due to its asymmetric nature, we opt for the median as a measure of center. Oh my God. I think I'm missing some information over there. Okay, I think this is it. There is a significant difference between the ages of patients who show up for the appointment and those who do not. In context, older patients are likely to show up for appointment compared to younger patients. What do you think about this? Isn't that very exciting? So it goes against what I've always been talking about. The older patients may not show up, which is not quite true. On the other hand, the younger ones are not showing up and the older ones are showing up. That's the power of analysis. Do you understand? And this alone gives you a very deep understanding as to how to build your model. There should have been a graph here. I think the code wasn't run. If you look at this, this code has been run, but this code wasn't run. Yeah, but then the output of the analysis is what we have here. So older patients are likely to show up for appointment, but younger patients are not showing up for appointment. Quite tricky, very, very tricky. Now, the last question is, how does the patient's gender associate with attending appointment? So what does the gender say? So from the above exploration, it shows that patient gender does not necessarily have any strong relationship with whether he or she will show up for appointment or not. I love this. So whatever intuition that you had in mind from the onset, if you do not explore the data, if you do not try to understand the data, you might be wrong. I started off by saying that females might tend to miss appointments because of this and this reason. And so that is the reason why I am putting gender there. Now I explore the data and then I'm telling you that it shows that patient gender does not necessarily have any strong association with whether or not they will show up for appointments or not. Do you get it? Very tricky, deviating from your normal rule of thumb. Now that is why data is very specific to use cases. It's not about what you think, it's about the use case at a very specific point in time. Or what you assume may not be the case. And that is why the processes that the data has to go through before you build a model has to be very unique to the situation or the space within which you are in. You understand? The last question, is there any association between receiving SMS alerts and whether or not patients show up for the appointment? Now the answer, SMS alerts do not guarantee patients' attendance to appointment. Surprisingly, there is no association between patients who do not receive SMS and appointment attendance. So SMS too is not determining anything, which means that there are reasons why patients are not attending, but SMS isn't part, the agenda isn't part, age is part because older people are attending more than younger people. What else again? Yeah, the month within which the appointment was booked isn't part, right? Exactly. So if I'm to remove features or if I'm to prune, these are the kind of things that I'll pay attention to and remove and then get new features to replace them or probably do some feature engineering around them, get different set of features that I think that may try to mimic or explain the situation a bit further, right? That is it. So next time we'll look at the ML bit of it, but for now, you would have to text me. Okay, then I think we've exhausted lots of our time already. Do you have questions before we close? Questions?
No, please.
All right, then. Okay, we just have 1 minute. I'll be waiting. If not, then we can call it a day. Network wasn't that good today, but anyway. Okay, so you get this notebook as well. Like I said, the focus isn't currently right now. The focus isn't the code that is here. The focus is on the story that this is telling. You get it. The focus is on the story that this is telling and the processes that this particular use case went through to understand the data. Now, data understanding is at the forefront of machine learning. If you don't understand your data, you go ahead and then you have to come and answer all these type of questions. So this is very important before you move ahead. All right. And how do you achieve this? These are some of the ways that you can achieve data exploration or go through data cleaning or data wrangling before you start ML development. So ML development isn't more like getting data and then just jumping through to select a model. No, get some understanding of the data itself. Understanding will tell you what features are needed and what are not needed. You understand? Great. There are no questions, and I think we can call it a day and then an evening actually. And then wait for our next VC.